All right, so with descriptive statistics behind us, we're ready to move on to kind of what would become kind of like, I guess, the meat, or if you're a vegetarian, the potatoes of kind of a general education kind of Stat 101 course, and that is this idea of inferential statistics. So, inferential statistics is doing what? Inferential statistics is how do we apply statistics. In particular, how do we take information from a sample and use that to draw conclusions about the population? So remember, we talked about this. We talked about this earlier on. This idea that right, we as researchers, as statisticians, are almost always interested in some characteristic of the population. That is, we want to know something about the population. However, generally the population is too vast, is too large for us to have any shot at all of looking at it in its entirety. So we don't give up, right? Statisticians never give up. What we do instead is we settle. We settle for taking a sample. We can't look at the whole of the population, so we look at a part of the population. We call that part of the population, we call it a sample. Now, we generate information from this sample, right? We measure some characteristic of the sample. We call this characteristic that we're measuring, we call it a statistic. And this statistic then becomes a best guess for the relevant matching characteristic of the population that we call a parameter, right? So the examples are the sample mean, that's a statistic, becomes our best guess for the population mean, that's a parameter. So the natural follow-up question becomes, well, how good of a best guess is it? Why are we justified in looking at a sample but using that to draw conclusions about a population, much of which we haven't even looked at, much of which we haven't even been exposed to? These are the type of questions that we tackle with inferential statistics, and it's what we're going to start laying the groundwork for doing right now. Now, there's sort of three key ideas, three cornerstones, three foundations to kind of exploring these important ideas of inferential statistics. The first one is the normal distribution, sometimes called the normal random variable, and coupled with that, this concept of standard scores. The second important key idea is that these statistics, remember, statistics are just attributes based on a sample, are random variables. So the sample mean is a statistic, the sample standard deviation is a statistic. These are all random variables. That's kind of the second key concept, the second big idea. The third key idea that's groundbreaking, that's life altering. I really don't think that's too big a phrase. In fact, if anything, I think I'm underselling it. That's miraculous, is this incredible thing, this gift from God called the central limit theorem that we'll explore in a future PowerPoint. So these are the three ideas that we're going to build upon. For this PowerPoint, we're going to really focus on that first one. So let's start with this idea of standard scores. A standard score, I didn't put its definition up here, but its standard score is the number of standard deviations a particular observation X is above or below the population mean. So remember, we have some symbols down there. That's the Greek letter mu, looks like the letter U, but it's actually the Greek letter mu. That's a common abbreviation for the population mean. And then in that denominator, we have the Greek letter sigma. That's an abbreviation for the sample standard deviation. So the standard score is defined as X, the original observation, minus mu. Remember, subtraction is a distance operator. So when we say X minus mu, we're really saying how far is X, the observation, how far is it from mu, the population mean? So we're looking at the distance between those two values. When we divide that distance by sigma, we're converting that distance into units of standard deviations. That gives us our z-score, our standard score, which tells us, again, how many standard deviations above or below the sample mean our observation is. So here's some examples, 3 of them, right? So everyone knows, of course, right? Walrus enthusiasts know that the average weight for a walrus, the population mean, the mu is 3,000. The population standard deviation, sigma is 250. So based on this information, equipped on this information, if we went on a field trip to the Philadelphia Zoo and we stumbled across a walrus who had a weight of 3,125 pounds, well, then their z-score would be 0.5, right? You could pause the PowerPoint, kind of do the calculations on a piece of paper, throw it into a calculator. You should get a z of 0.5. What is that z of 0.5 saying? It's saying that that particular walrus's weight is half a standard deviation above the mean. We could probably see that for ourselves. So our second walrus has a weight of 2,500. We compute her standard score. We get a standard score of -2. Wow, -2. So that's basically saying that she weighs less than the mean. How much less? Well, she weighs 2 standard deviations less than the mean, right? We know it's less because it's negative. Our third walrus is Black Bart. Oh man, Black Bart is a brute of a walrus, right? Never a more foul-tempered, black-hearted walrus will you ever meet. And Black Bart weighs 5,000 pounds. Oh my. 5,000 pounds. And if you do the math, and if I did the math correctly, and you compute Black Bart's standard score, you get a standard score, a z-score of 8. Wow. 8. Now that's something to talk about. So why do we care? What's the point of taking something, taking some number, and turning it into some other number, right? Why do we take something that has a natural kind of unit like weight and turn it into some maybe kind of a little bit more abstruse unit, which is these kind of standard deviations? Well, it turns out that standard score is coupled with something called the empirical rule. We're going to talk about the empirical rule on the next slide. It turns out that standard scores coupled with the empirical rule help us as researchers determine the worth or value of a particular score or measurement. That is, to a researcher, units of standard deviations are kind of our natural measuring stick. And to get a sense of why that is or how that is, let's go to the next slide and look more closely at this empirical rule. So the empirical rule says this: for a symmetric, I don't know why I used that phrase mound shape, whatever book I copied it from must have used mound shape. It's probably more commonly referred to as bell shaped. So for a symmetric mound shaped, bell shaped histogram, the following facts are, a little bit of rounding, true. 68% of all data values are within 1 standard deviation of the mean. 95%, so a lot, almost all, of all data values are within 2 standard deviations of the mean. And finally, 99.7%, virtually everything, virtually everyone, virtually the whole world lives within 3 standard deviations of the mean. So the empirical rule, what? The empirical rule is kind of what we use to kind of develop a little bit of statistical literacy, to develop a quantitative sense about how rare or remarkable observations occurring in nature are. Because what? Let's assume, and admittedly this is a big assumption, but let's assume that human heights follow a bell-shaped distribution. Then what we're basically saying is almost all of humanity, 99.7% of humanity, lives within 3 standard deviations of the mean. So if somebody's z-score, remember the z-score is measuring number of standard deviations from the mean, if somebody's z-score is more than 3 or less than -3, that's particularly noteworthy, isn't it? That is, they're like an Einstein of whatever it is we're measuring, in this case height. So if we go back to kind of the previous slide, and in particular we think back on Black Bart, right? If I told you that I went to the Philadelphia Zoo and I saw a walrus that weighed 5,000 pounds, you probably would not know whether or not to be impressed. Is that a lot for a walrus? Who knows? Maybe that's a little for a walrus, right? We're not really sure. But if I told you that I went to the Philadelphia Zoo and I saw a walrus whose weight was 8 standard deviations above the mean, you would stop and you would take notice. You would say, wow, that is impressive. That is a once in a lifetime walrus, right? That's like the Halley's Comet of walrus. 8 standard deviations is almost unheard of. So again, 5,000 pounds, it's hard to know what that means. But a z-score of 8, we know that that's a big deal. And that's thanks to this combination of standard scores and empirical rule. Now, moving on from standard scores, I want to talk about the normal random variable. Before I talk about that, I want to talk very briefly about just random variables in general. So what is a random variable? A random variable is this abstract notion of a random phenomenon that takes certain numerical outcomes with certain probabilities, right? So just some random phenomenon that takes certain outcomes with certain probabilities, certain numeric outcomes. This mapping of the outcomes it takes and the probability of those outcomes, we refer to that as the probability distribution. So all random variables have one, a probability distribution. Now, I'm going to go ahead and just say all random variables have a mean and a standard deviation. Yes, there are strange, unusual, pathological exceptions that kind of lurk on the fringes of reality. The Cauchy distribution, for example. But most of the random variables that we're going to work with in this course and future courses have means and have standard deviations. So most random variables have A, a probability distribution, B, a mean, C, a standard deviation / variance. Now, random variables fall in one of two categories. Again, this is not a mathematically perfect definition, but it's a good applied working definition. Discrete random variables we can think of as random variables whose outcomes take whole numbers. So if you think of the number of siblings of a randomly selected student, you can have 1 sibling or 2 siblings or 3 siblings. You cannot have 2.7 siblings, right? You're only taking those whole numbers. Whereas continuous random variables are random variables who take values over a range of values, an interval of values, a continuum of values, right? So if you think about the weight of a randomly selected student, a student can weigh 160 pounds, a student can weigh 161 pounds. But if we had a precise enough scale, a student could also, in theory, weigh any number between 160 and 161, right? So that would be an example of something that we might model with a continuous random variable. Now, going back to that idea of probability distributions, sometimes we use the word random variable and distribution interchangeably because a random variable is uniquely defined by its probability distribution. So, right, we're going to talk a little about the normal random variable, but I often call it the normal distribution because it's defined by the probability distribution associated with it. That probability distribution, we call it the normal distribution. So of all the random variables, the many wonderful random variables that are out there ranging in the wild, the normal random variable is probably the one that we use most often and most commonly. We'll see why when we talk about the central limit theorem down the road. The normal random variable is an example of a continuous random variable. It's also an example of a random variable that has a mean and a standard deviation. It can have any mean and any non-negative standard deviation. Now, for now, we're actually going to focus on one specific type of normal random variable or normal distribution, and that's something that we call the standard normal. We typically use the letter Z to refer to the standard normal. And the standard normal random variable is just a normal random variable with a mean of 0 and a standard deviation of 1. Now, right now, this seems a little bit weird because what kind of real-life phenomenon would have a mean of 0 and a standard deviation of 1? Right? We can't really think of a lot of them. So why then are we studying this? Why then is it important? I promise you, it will become very apparent why it's important. But for now, to give us a little bit of of applied scaffolding to give a little bit of context to kind of the next few slides. Let's just think of Z, let's think of this random phenomenon Z as like a test, right? So we have a test and a student takes the test and we don't know what they're going to get, right? They can get any score on the test. And let's say that's kind of a weird test. That is, you get a question right, you get points added to your test, but you get a question wrong, you get points subtracted from your test. And it turns out because of this system, it's possible to get a negative score. In fact, it's a tough test, right? So students on average get 50%, which is kind of like breaking even. So that's like a score of 0. So let's think of this Z as just like the score on a test. Are we okay with that? And then we can kind of use that as kind of like a little bit of framework for the questions that are coming up. Now, one of the key skill sets that we need to develop as fledgling statisticians is the ability to calculate normal probabilities. How to find probabilities of a normal distribution. If someone takes this test, what's the probability they score more than 1 or less than 1 or get between -2 and +3, right? How do we calculate these types of probabilities to see how likely or unlikely a particular event or occurrence may be? Well, for now, we're going to focus on using tables to find these probabilities. Now, there's tables in the back of our textbook. These tables are a little bit different because I like these tables. These tables use what's referred to as a CDF. CDF just means cumulative distribution function. It's used a lot in the study of probability. You have CDFs for any random variable. And the CDF basically says for that random variable, the CDF for a particular value A says just what's the probability of this random variable being less than or equal to that value A. So our tables give us CDF values for positive values of A and also negative values of A. You might want to pause the PowerPoint here. It's up to you. It might be worth actually printing out the PowerPoint tables, the tables you'll see on the next 2 slides. May or may not be worth printing them. If you have 2 monitors, you could put one of them up on your second monitor, so that you could refer to those tables as we go through different. I mean, calculations is a strong word, but as we solve problems throughout this PowerPoint, you can have the tables handy to look at. If you go, I think like 3 slides down, you'll see that there's some links, and the links go to the web pages where I pasted the things, but that's where you could print the tables from. If you're inclined, it's entirely up to you. So here's the first table, and right before we kind of dive into the table, I want us to take a look at that shape up top. So there's that bell-shaped distribution. That's what a normal distribution looks like. So when I say that something follows a standard normal, what am I saying? I'm saying, well, first off, right, the standard normal is always centered at its mean, or a normal distribution is always centered at its mean. So a standard normal has a mean of 0, and if we look at this particular curve, we'll see this curve is centered at 0. The idea of it being symmetric means that those 2 tails match up perfectly. If we were to fold that bell shape up, if we were to kind of fold it along a crease at 0, those 2 tails would match or overlap perfectly. Now, when I say that something has a normal distribution, say this kind of weird exam, all I'm saying is that if maybe 100 or 1,000 students took this exam and we recorded the scores for that 100 or 1,000 students and we made a histogram of those scores, that histogram is going to look, well, like that nice smooth distribution up there. That histogram is going to have that nice, smooth, symmetric bell shape to it. That's all we're saying when we say that something follows a normal distribution. Now, that picture is reinforcing another key idea, and that key idea is that particularly for continuous random variables, we can think of area and probability as being synonymous with one another. Area is kind of our proxy for probability. So what we've colored in that picture, well, we've colored in everything to the left of the value of 1. So that area is the probability that Z is less than or equal to 1. We can find that area using the table below the picture. We just have to look up the value 1. Well, 1.00. So we start in that leftmost column. We go down, 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 way downtown, until we get to 1.0. That gets us to the 10th place. We then need to go over to the 100th place. That's where you go over. That's where you move to the right. So we actually just need 1.00. So we go 1.00. That's 0.8413. So that basically, that table is telling us there's an 84% chance of getting a 1 or less on this particular exam. What if I wanted to know the probability of getting less than or equal to 1.52? Well, I go down to 1.5, then I go over to 1.52. And then if my eyes are reading that correctly, I think we get 0.9357. So that's saying the probability of being less than or equal to 1.52 is 0.9357, right? You have a 93.5% chance of scoring less than or equal to a 1.52 on this particular exam. Easy enough, right? So that was for all the positive values of z, all the values to the right of 0. This is for all the negative values of z, all the values of z to the left of 0. It works in the exact same way, right? So if you wanted to know the probability that z is less than or equal to negative, say, 0.75, this is really challenging myself, negative 0.75, I believe that should be 0.22663. So there's about a 22.7% chance of scoring less than or equal to negative 0.75. Now here's a concept check for you. All the probabilities on the previous table were 0.5 or more. All the probabilities on this negative table are 0.5 or less. Does that make sense? It should. In terms of developing an intuitive understanding, a graphical understanding, a visual understanding, right? The fact that all the values in the previous table are positive and all the values of this table are, all the values in the previous table are more than 0.5 and all the values in this table are less than 0.5. That should make a lot of sense to you. And if it doesn't, well, keep going through the PowerPoints, work some problems. If it still doesn't make sense, come talk to myself or one of the graduate assistants, because that's a big conceptual disconnect that we need to remedy. And as promised, here's the links to those tables if you wanted to pull them up yourself, to have them on another monitor or to print them up to work with. And so here's a little bit of practice problems for us, right? So this is just using those tables, practicing with those tables. The probability that z is less than or equal to 0. Well, 0 is that mean, right? So 0 is right smack in the center of that thing. And if you look up the value 0, you get 0.5. Which should make sense due to the symmetry, right? 50% of that area is to the left of the mean, which is equivalent to saying what actually? It's equivalent to saying that the mean is the same as the median. It's kind of cool. What about if we wanted the probability that z is less than or equal to negative 3? Well, it's a negative value, so we have to use the second table. That's our negative table. We go down to the negative 3.0 column. We just go over to negative 3.00, and it should be 0.00135. So like a 0.1% chance of that happening. It's not particularly likely. It's very rare for someone to score that badly on this exam. What about the probability that z is less than or equal to negative 2.73? So this is just go down to the negative 2.70, then go over to the 0.03 column, and we should get 0.00317. Again, right, hopefully you're pausing it, you're verifying these things. You need to be able to do it yourself, so make sure you understand where these numbers are coming from. Next is the probability z is less than or equal to 1.76. Again, now we have to go to the positive table because that's a positive number. We go to the 1.70 down, 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 down to 1.70. Then we go over to 0.06. That's going to give us 0.9608. Now, the next bullet point, it kind of illustrates kind of a key quirk, an interesting quirk, not just of the normal distribution, but of any continuous distribution. And that is, for any continuous distribution, the probability that z is less than or equal to some number, say 1.76, is the exact same as the probability that z is strictly less than 1.76. Because remember, probability is area, and in terms of that bell curve, just a single point, 1.76, has no area. So like what does this imply? It implies an interesting sort of side fact, that the probability z equals 1.76 is 0. That is, for a continuous distribution, the probability that it equals a specific number is always 0. The probability z equals a for any number a is always 0. And then one of the implications of that is our fourth and fifth bullet point. That less than or equal to and strictly less than means the same thing. We could be a little bit sloppy with it. We could be a little bit lazy with it. Now, the last two bullet points are some nice conceptual checks for us. What's the probability that z is less than or equal to -5? Hey, in BD, no big deal. I'm just going to pull out my negative table because that's a negative number. I'm just going to go down to -5.0 and, oh dear, there is no -5.0 on the table. Oh my. We just broke the table, didn't we? So what's the answer? Is the answer indeterminate? Is the answer, as of yet, unsolved by modern day statisticians? No. What is that answer? Nice. Good job. Hot dang. You got it. The answer is going to be, right, very, 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 very close to 0. Not exactly 0, but almost like immeasurably close to it. Because again, right, we could just draw that picture. We draw that bell-shaped curve. We go way down that leftmost tail to -5, and we want the area. Remember, probability and area are synonymous. We want the area associated with being less than or equal to -5, and that's just going to be a very minuscule amount of area. Something very, very close to 0. What about that last bullet point? What about the probability z is less than or equal to 5? Another concept check. We look up 5 in our positive table and it's not there. Hot damn, or pardon my French, hot dang, right? You did it again. The answer is going to be, you're absolutely right, it's going to be very, very close to 1. Again, we draw the picture. You draw that curve. Positive 5 is way over in the rightmost tail, and we want everything less than, everything to the left of that. So if you color that in, you're coloring in almost the entirety of the bell curve. Right? You're coloring in almost all of the bell curve. So, right, that's close to 100%. Not exactly 100, but very, very, very close. Almost immeasurably different than just the value 1. Now, as I like to use a very common acronym, abbreviation, when I'm doing these probability questions, I encourage you to really kind of live by this motto, to live by this acronym, APIOBUF, right? APIOBUF. Everyone knows what that is, right? It just stands for a picture is our best friend, exclamation. A picture is our best friend, right? Because why? Like, I don't know about you, but when I'm faced with a problem and I'm not sure how to solve it, what do you do? What I do is I call a good friend. I call my best friend. And I find that my best friend is always there for me, and I find that my best friend always helps me solve the problem. And when we're working with normal probability questions, there's no better best friend than a picture. When you're not sure how to solve that problem, then pull up your old friend, the picture, and that friend will be there for you, and that friend will solve the problem for you. APIOBUF. If you haven't already, draw the picture that corresponds with all the bullet points from the previous slide. So the tables allow us to directly answer the question, what's the probability z is less than or equal to some number for just about any number? But what if we're asked for the probability of getting more than something, right? So we can answer questions like what's the probability of scoring less than something, but what if we want to find the probability of scoring more than something? Well, this is actually a really cool kind of like manifestation, or a real cool example of classic textbook mathematical reasoning, right? We're presented with a new problem, something that we haven't been exposed to, something that we're not sure how to solve. And so how do we do it? Well, we try to be clever, we try to be inventive, we try to be innovative. We try to find a way to take this complex problem and break it down, to re-express it in terms of problems that we already have mastered, that we already know how to solve. So it turns out that we can re-express these greater than problems in terms of CDFs, in terms of less than or equal to problems. Kind of cool, right? So if we wanted to find the probability that z is greater than or equal to some number b, it turns out, math fact, that that is 1 minus the probability z is strictly less than b. And remember, for continuous distributions, z strictly less than b is the same as z less than or equal to b, so we can just grab that from our table. Does that make sense? We can see it a few different ways, and again, it's a nice conceptual check. That second bullet point, we can algebraically rearrange it, can't we? And if we algebraically rearrange it, it basically says probability z greater than or equal to b plus the probability z is less than b equals 1. That makes sense, right? The probability that z is, say, greater than or equal to 3 plus the probability it's less than 3 is 100%. It has to fall into one of those two circumstances or categories, doesn't it? And then if we rearrange that, then we get that second bullet point that we're looking at right now. So it should make sense sort of algebraically. It's got a rule like law of complements or something like that. But it should also hopefully intuitively make sense graphically. You should be able to convince yourself, verify this using a picture. So to make it a little bit more concrete, if you wanted to find the probability that z is greater than or equal to 0.4, the probability of scoring a 0.54 or higher on this test, well, that's 1 minus the probability that z is less than 0.54. We can get the z less than from our table, so that becomes 1 minus 0.7054, so you get not quite 30%. Again, draw the picture and use the table yourself and verify that answer. The picture helps, doesn't it? That picture is a hell of a best friend. That picture deserves a promotion, right? Maybe instead of being our best friend, maybe instead of Appy Buff, it could be Appy Buff. A picture is not just our best friend, a picture is our best friend forever. Here I am, 10, 15, 20 years later, since I was in kind of your position, sitting in a chair, learning normal probabilities, still my best friend, and hopefully 20 years from now, it's still your best friend as well. And so the last sort of situation that we need to worry about is this. We know now how to do the probability z is less than some number. We know how to do the probability that z is more than some number. The third sort of possibility is what's the probability that z is between two numbers. And again, there's the fact, there's the formula, there's the truism, but I want you to draw pictures and try to convince yourself. It's maybe a little less intuitive than the previous PowerPoint or the previous slide, but still, you should be able to kind of use pictures to convince yourself that this is sensible. I don't want you just to blindly memorize it. I want it to make sense to you. That the probability that z is between a and b is the probability z is less than or equal to the larger value b minus the probability z is less than the smaller value a. If that doesn't make sense to you, come talk to me or come talk to one of our graduate assistants. We can draw you some pictures and we can kind of show you kind of why that is. So as an example, the probability that z is between 1 and minus 1, Well, that's just the probability that z is less than or equal to 1 minus the probability z is less than minus 1. We can look up now both of those numbers. We've broken it down in terms of our tables. So we use our tables now. We get 0.8413 minus 0.1587, and that gives us 0.6826. Hey, 6826! Holy deja vu! We've seen that number before, haven't we? We actually knew the solution to this problem before we even got started. Because what is that really asking us, right? The probability that z is between 1 and minus 1 is really the same as asking, what's the probability that we're within 1 standard deviation of the mean? And we know from the empirical rule that that's 68%, don't we? And so we shouldn't be surprised by that slightly more precise answer to the question. Pretty cool, right? I don't know about you, but I really feel drawing the pictures really helped me out. Heck, I don't hope that 20 years from now you're still best friends with these pictures and still drawing them and having the time of your life. I hope that when you're there and you're on your deathbed, when it's your funeral, that picture is right there with you, just comforting you and being there for you. A picture is not just our best friend, not just our best friend forever, it's our best friend forever ever, right? Happy a buffet. Yeah, never forget to draw those pictures. As long as you take the time to call them and to draw them, I promise you, to the day of your death, they'll always be there for you. Now, let's transition a little bit, although we may or may not have earned this transition. If you're a white belt and normal probabilities, I want you using those tables. However, at some point you're going to use the tables and use the tables and use the tables. You're going to become a black belt. Well done, grasshopper. And at that point, you can start using software to answer the questions. But until then, I want you to use the tables. Now, sometimes students say, like, well, what the cut though? Why? No real-life practicing statistician uses tables. It's just not done. Any real-life statistician who needs to solve a probability question is going to use some kind of software package to do it. True, you're right. However, I would counter you in the following way. I guarantee you this. Any successful working statistician knows how to use the tables. And that's what's important. If you don't understand how to use those tables, then you don't understand this important idea about distributions and, more importantly, the equality of probability and area and how we sort of use them as interchangeable concepts. If you do not understand this important key concept, if you do not internalize that, if you do not embed that into the heart and fiber of your very being, then you are not going to understand the next concept, and you are not going to understand the next concept, and you are not going to understand the next concept. Yes, you could sort of mindlessly answer a probability question using a software package, even if you do not understand how those tables and how those pictures work. But if you want to be a successful statistician, you have to understand the underlying mechanisms. Why is it working this way? How is this software coming up with these probability questions? You need to know that. And once you've learned that, you've earned the right now. You've earned the right to use a software package as a shortcut. But you need to put in the time to develop the intuition. Now, I know a lot of you probably have put in the time in Stat 505/504, because I think that you did a lot of these problems there, and of course a lot of you have taken introductory stats classes even before then. However, a few of you probably have not done this, or it's been a long time. And if that is the case, I want you using those tables solving these problems. But once we've perfected the tables, well, this is how we do it in SAS. We can actually use the CDF cumulative distribution function. You can specify the distribution you want to use, in our case the normal. The first input, the first number 2, is what we want the probability of being less than or equal to of. So here we're asking the probability of being less than or equal to 2. And then you could do it for any mean and any standard deviation. We've been focusing on the standard normal, so we would put a mean of 0 and a standard deviation of 1. And we do all that, and we do a proc print, we get the number 0.97725, which is what? It's very, very close to 0.975, which actually, if you draw a picture and use the empirical rule should give you 0.975 as the answer. That's a good concept check for you as well. Can you get that? Can you get 0.975 from the empirical rule? Now we're getting 0.97725, which means that the empirical rule again uses a little bit of rounding. The 0.97725 is a slightly more precise answer. Now, doing this kind of stuff always feels awkward to me in SAS. We only have Citrix SAS, so you gotta go to the web page and log in and do all that stuff. It's a lot of work, and you wait for it to work, and sometimes it doesn't work. Then you create a data set, you embed the answer in the data set. I promise you, if it's so much easier to do this type of stuff in R. So if you're not proficient in R yet, this is one of many reasons to start building that proficiency. You can, of course, install R for free on your computer, and rather than have to go through the whole cloud and the Citrix and do I have internet access, you can just pull it right up right away no matter what, and you could type in the following code. pnorm 201. So by default, it uses the CDF function. First input is what you want the value less than or equal to of. So here, same thing, we want less than or equal to 2. And we want normal distribution with a mean of 0, standard deviation of 1. So pnorm, I want the probability of a normal distribution being less than or equal to 2, where the mean is 0 and the standard deviation is 1. You type that in, you hit enter, and R is just going to give you the answer. You have to admit, even if you're a SAS enthusiast, even if you're a SAS lover, that's a lot easier than kind of the awkward steps we had to do in that previous slide. Stop! In the name of statistics. There is a PDF posted on D2L right now entitled Practice Problems 1. Now I'm leaving it up to you. If you've already perfected all this stuff, then don't worry about it. Go on to the next narrated PowerPoint. No big deal. I know that all of this has probably been done in 505, 504. If you've taken that class, you're probably fine just going to the next narrated PowerPoint. However, if you have not taken 505 or 504, then I want you to practice these problems. So in that PDF, I want you to do the problems from sections 7.1 and section 7.2. I say use tables as necessary because some of the problems are standard score problems. You don't need tables for standard score problems, but anything that asks you for a normal probability, use the tables. And then when you think you've mastered those skill sets, well, then do them all over again using a software package, maybe SAS, maybe R, to perfect the skill of doing them in a software package. And if you need to check your work, the answers to all of the odd problems are at the very end of that PDF. So if you scroll to the end of the PDF, you should see the answers to all of the odd problems. And if you got all the odd problems right, no pun intended, odds are you also got the even problems right as well. So good job, Grasshopper. One PowerPoint down and however many more to go.